let's talk about this K, this thermal conductivity. And that thermal conductivity is really a measure of a material's ability to conduct heat. All right, and really you want to think about this as a property of the material. So like I said earlier, certain metals, say aluminum or copper, are going to have a higher thermal conductivity than something like styrofoam. And we don't have to worry about what size that is. It doesn't matter how much aluminum I have or how little styrofoam I have. The thermal conductivity is a property of the material. Whereas here I'm going to introduce two new variables that are going to be based on the actual dimensions that you have for a material. So R is going to be the thermal resistance, and C is going to be your thermal conductance. So R is the inverse of conductance, and conductance is the inverse of resistance. So really that R, sorry, my iPad is falling over here. R is equal to 1 over C, if you heard any sort of crash, or C is equal to 1 over R. You may also see this C be U. We have so many things that are U, and so I don't really love that. We have a lot of things that are C too. So just be careful if you see one or the other, it might be interchanged. In this case, I'm going to use C, but you can see U as well. And these properties are really telling us about the ability of a material based on those actual dimensions of the material. So let's look at the equations to give you an idea of what this actually looks like and why thermal conductivity isn't based on size, but resistance and conductance are. And I also want you to think of a tie to electrical knowledge. Think about electrical conductivity and electrical conductance and how that might parallel with this relationship as well. So equations, we have for K is equal to, I'm going to give you two different versions based on those Q's we just talked about. K can be equal to L over delta T times little q, or it can be equal to big Q, L over delta T A. And let me actually say here too as well, I changed variables a little bit, but that L is actually just delta X if we're looking at our equation above. That's another one it switches between. Sometimes you'll see L, sometimes you'll see delta X. So that's something to also be aware of. So there's our equation for K. So you see that just comes directly from our equation that Q is equal to Ka delta T over delta X. Okay, so for R, we're still going to use that equation. So we're going to use Q is equal to Ka delta T over delta X, but we can rewrite that as delta T over, let me make this bigger again, delta T over delta X over Ka. So if we pull this bottom variable right here, delta X over Ka, this is going to be our resistance, our thermal resistance. And that's just a convenient grouping of that thickness over the thermal conductivity times area. This is another place you again have to be careful with that little q coming in again, because R can be equal to delta X over Ka. It can also be equal to delta T over little q, which then brings it equal to L over K if we're going to look at the specific resistance versus the including the area. So it can be a little confusing. This is where it's critical that you write down your units and make sure they cancel, because sometimes you might have little q, sometimes you might have big Q, and it can get really confusing. So let me actually write this here to make this a little clearer. So R is equal to delta T over little q, which is equal to L over K, or we have R is equal to delta T over big Q, which is equal to L over Ka. So it's whether or not that area is included can make it very confusing. So if we think about conductance, that's just going to be exactly the opposite. So we can think of this as R is equal to little q over delta T equals K over L, or R is equal to big Q over delta T is equal to L, or Ka over L. And again, I started using that L again, so it could be delta X here as well for L. Okay, so remember that big Q is overall heat transfer. Little q is the specific heat transfer per unit area. So, got to think about those units and how that plays out. And that will really come in, well, thinking about common units here. Let's go through that before I look at typical values. So, units here are going to be, typically for K, are going to be watts per meter Kelvin, or BTU per hour. So BTU per hour is kind of your equivalent to watts. You'd have to look up the specific conversion factor. I don't know off my head how you can go from BTU per hour to watts. Or I mean times degree Fahrenheit times foot. So if that's not a weird unit for you, I don't know what is. Typical units for C, we're going to jump to. So let me put kind of a little box around here. These are going to be our units. So our units over here for C are going to be BTU per foot squared, degree Fahrenheit, hour, or watts, meter squared, Kelvin. And R is just going to be the inverse of that, which will be feet squared, degree Fahrenheit, hour over BTU, or meter squared Kelvin over watt. And let's talk about the meaning of this. The units of resistance are confusing to think about the physical meaning. That's really why we have the conductance. It's because if you think about having 1 foot squared of something, let's say that this has an R value of 10. If we think about conductance, that's going to be equal to 1 over 10, because we know that conductance is equal to 1 over R, so that's going to be 1 over 10. And then thinking about the units, that's going to be BTU per foot squared, degree Fahrenheit, hour. So for every foot squared, so say this is 1 foot squared, for this 1 foot squared, there's going to be 1/10 of a BTU lost for every degree Fahrenheit of delta T there is per hour. So those units make more sense than thinking of them in feet squared, degree Fahrenheit, hour per BTU. Think about the flip, the actual conductance, what that means. So as R goes up, as we get a higher resistance, we're going to get a lower conductance, which makes sense. If something is higher resistance, it's a worse conductor. Whereas if it's a lower conductance, we're going to get a higher resistance. So there you go. Thinking about that meaning. Hopefully those pauses helped you think through those a little bit. So let's finish with talking about typical values. And this is where I'm going to say that it is, again, confusing with units because I just talked you through the typical units, but if you go to tables, they're going to have all sorts of different units available. And you just have to check what these actually are on the tops of tables because they can differ. People label them differently. Little q, big Q, Q dot. What did they use? We got to figure it out. Just check your units. Always write your units out. So for K, you see something like copper is very high, 400. So there are 400 watts per meter times Kelvin. So that's 399 watts for every meter of thickness. And thinking about that temperature difference per temperature difference Kelvin. Whereas if we go to something down like plastic, we know that plastic isn't as good of a conductor as copper. So we're getting a lot less watts of heat transfer per meter thickness per Kelvin, or that Kelvin difference between the hot and the cold side. And if you look at something, this is something I find interesting, that water is 0.6 versus ice is 2.22. So ice has a higher thermal conductivity than liquid water. Air is very, very low thermal conductivity, so it's not as good of a conductor. So interesting to look at there. So then we can look at the resistant R values that we get. Again, check your units here. I wrote Kelvin per watt because this is just another one of the units you may see, but make sure to check it because you can also see them in BTU per foot squared degree Fahrenheit hour. Oh, that's C. Let's bump that over. I always make that mistake. So this is C. And again, you could see this in that meter squared Kelvin over watts. So just depending on, again, on that meter squared or that feet squared, it's going to make a difference. So thinking about R values, the trends are still going to be the same regardless. If we think about this thickness of 8-inch concrete versus 12-inch versus 24-inch, this is going to differ. Your resistance is going to differ. You get 1.1. So not a super high resistance. If you think about looking at the watts per Kelvin instead of the kelvins per watt, or you can think again in these units, 1.1 BTU per foot squared degree Fahrenheit. So that's only 1 over 1.1. Right around 1, basically. Whereas if we do 1 over 11 for fiberglass, we're losing a lot less heat. We're losing a lot less BTU per hour for that square foot for every degree Fahrenheit of difference. Glass, again, we're going to get a number greater than 1, that 1 over 0.023, because we know that that resistance is very low in glass, which is going to give it an even higher conductance. So you can compare that like when we're thinking about glass or air, which have smaller values than something, say, polystyrene, or something like commercial windows, where we're really trying to keep either the hot outside and the cool inside, or the hot inside and the cool outside. You want a much higher resistance, which is going to give you a much lower conductance if we look at, these are simply the inverse values. So bring your questions. There may be some questions. The units on this is probably one of the most challenging things because we have to think through that Q dot, big Q, little q, what are we actually looking at? But just think of these values and these relationships. That's one of the most important part here, is thinking about why concrete and may be different than fiberglass, and why fiberglass is different than regular glass, and why a single pane window is a lower resistance than a double pane window. But then when we do the inverse, the single pane window is a higher conductance than a double pane window. So thinking about those relationships, let's come back and talk about any questions that you have.